Science is not in the business of proving things impossible. Science is in the business of figuring out what is more likely and what is less likely given everything we actually know about the world. That's the game. That's the whole game. And when you play that game honestly, and when you sit down and look at the real numbers, the real distances, the real physics, what you find is not that alien visits are impossible. What you find is something far more interesting and far more humbling than that. What you find is that the universe is so unimaginably, grotesquely, almost insultingly large that the very question, why haven't aliens visited us, turns out to be a little bit like asking why your neighbor in Tokyo hasn't stopped by for coffee this morning. The answer isn't that your neighbor doesn't exist. The answer is that Tokyo is very, very far away and nobody has invented a way to get here before breakfast. So let's talk about that. Let's actually sit down and look at the numbers, because the numbers are where the real story lives, and the real story is more wonderful than any flying saucer. Now, the first thing I want to do is give you a feeling, not just the words, but a genuine feeling for how big space is, because I'm convinced that when most people hear the word light year, something goes wrong in their brain. The word comes in, the brain says very far, and then the brain moves on. But very far is not doing the work here. Very far is doing almost none of the work. So let me try something. Light travels at 300,000 kilometers per second. Now, when I say that, you might not. Sure, 300,000 kilometers per second fast, but let me give you the feeling of it. And the moon is about 384,000 kilometers away from Earth. Light makes that trip in about 1.25 seconds. You blink and light has gone to the moon and is almost back. Now, the sun, 150 million kilometers away, light makes that trip in about 8 minutes. 8 minutes. You make a cup of coffee, you sit down, and the sunlight hitting your face right now left the sun while you were still in the kitchen. And that's inside our own solar system, our own cozy little neighborhood. Now, Voyager 1, this is a spacecraft we launched back in 1977. It's the farthest human-made object from Earth that exists right now. As of today, that thing is about 163 astronomical units away. That sounds impressive. The problem is that 1 light year is about 63,000 astronomical units. So in roughly 46 years of travel, Voyager 1 has covered about 1/390 of a single light year. At the rate Voyager 1 is going, it would take roughly 75,000 years to reach the nearest star. 75,000 years. That's not a generation ship. That's not a generation ship, and 1,000 more generation ships after it. Human civilization as we know it is maybe 10,000 years old. We're talking about 7 times the entire span of recorded human history just to reach the star next door, and that's the nearest star. So let me tell you about Proxima Centauri, because this is the star everyone brings up, Proxima Centauri. It's the closest star to our sun. And when people say the closest star, something feels reassuring about that, like, okay, at least that one's accessible. The closest one is close. It is 425 light years away, which means that light, the fastest thing there is, the speed limit of the universe, the thing that nothing with mass can ever reach, light takes 4 years and 3 months to make the trip. If you somehow managed to build a spaceship that traveled at the speed of light, which you cannot because of special relativity, but just as an exercise, you would be old by the time you arrived. You'd arrive at the nearest star as an old person if you left as a young one. And of course, you cannot travel at the speed of light. As you go faster, your effective mass increases. The energy required to keep accelerating climbs. By the time you get close to the speed of light, the energy required to go even a tiny bit faster approaches infinity. Nature is being very serious with you here. It is not a suggestion. You cannot go the speed of light. So, in practice, the nearest star is more than 4 light years away, and you cannot get there in a human lifetime with any technology we can even theorize about right now. Now go a little further. Sirius, the brightest star in the night sky, the one people have been looking at and naming and navigating by for thousands of years. Sirius is 8.8 light years away. Vega, another famous bright star, is 26 light years away. The Orion Nebula, that beautiful fuzzy patch in Orion that people photograph and put on posters, the light you're looking at left that nebula 1,500 years ago. You are looking at the Dark Ages. You are looking at a picture of a place that was taken when Europe was falling apart and the Roman Empire was collapsing. And none of these things are anywhere near the edge of our galaxy. The Milky Way, our galaxy, is about 100,000 light years across. The center of the galaxy is around 26,000 light years from where we sit. And there are estimated to be somewhere between 100 billion and 400 billion stars in this galaxy alone. Just our galaxy. Beyond that, the nearest big galaxy, Andromeda, is 2.5 million light years away. The light hitting your eye right now from Andromeda started its journey before Homo sapiens existed as a species. You are in the most literal and physical sense possible looking at the past. You're using your eyes as a time machine. And the observable universe, everything we can possibly see from here, contains something like 2 trillion galaxies. 2 trillion, each with hundreds of billions of stars. Now here's where I want to introduce you to a lovely little piece of scientific thinking called the Drake equation. A fellow named Frank Drake back in 1961 sat down and said, okay, let's try to estimate how many civilizations there might be in our galaxy that we could communicate with. And he wrote down an equation. The idea is simple and elegant. You start with the rate at which stars form in the galaxy, a few stars per year. Then you ask, well, what fraction of those stars have planets? Then of those planets, how many are in the habitable zone where liquid water is possible? Then of those, how many actually develop life? Then of those, how many develop intelligent life? Then of those, how many develop technology capable of communication? And finally, how long do such civilizations last? You multiply all those fractions together and out comes n, your estimate of how many communicating civilizations exist in the galaxy right now. Now, some of those early terms we've actually gotten much better at estimating. Thanks to the Kepler Space Telescope and other missions, we now know that essentially every star has planets. Every star. When you look up at the night sky behind each of those points of light, there is at least one planet, probably several. Of stars similar to our sun, about 1 in 5 has a planet in the habitable zone. This is genuinely remarkable. The universe is apparently very fond of making planets, so that part of the equation looks pretty good. There are a lot of planets. There are probably hundreds of millions of potentially habitable planets in our galaxy alone. But then you get to the harder terms. What fraction of habitable planets develop life? We have exactly one data point, Earth. That's it. We have one example. You cannot build a reliable probability estimate from one data point. You can have intuitions, you can have guesses, but you cannot have science, not yet. When I was taught statistics, my professor said something I've never forgotten. One example tells you that the thing is possible. That's all it tells you. To get a probability, you need many examples. And the term that is absolutely the most uncertain of all is the last one. How long do technological civilizations last? Because here's the uncomfortable thought hiding inside the Drake equation. If civilizations typically destroy themselves through war, environmental collapse, whatever, shortly after developing advanced technology, then at any given moment there might be very few of them around. The galaxy might have been full of civilizations that came and went before we got here, like flowers that bloom and die on a hillside, never overlapping. Whereas if civilizations typically last for millions of years, then the galaxy might be absolutely teeming with them right now, and the question becomes very different. The Drake equation doesn't give you an answer. It organizes your ignorance. It shows you exactly where the uncertainties are, and it turns out the uncertainties are enormous. N could be 1, N could be 1,000,000. Honest people disagree, and they disagree because the honest answer is that we genuinely don't know. Now, here's the thing that I find most fascinating about all of this, and it's something called the Fermi paradox. Enrico Fermi, brilliant physicist, one of the best minds of the 20th century, was having lunch with some colleagues around 1950, and the conversation turned to extraterrestrial civilizations. And at some point, Fermi put down his fork and asked a very simple, devastating question: where is everybody? Think about what that question is really asking. If there are hundreds of millions of potentially habitable planets in just our galaxy, and if the galaxy is roughly 10 billion years old, then there have been billions of years for civilizations to arise, develop technology, and spread. Even at modest speeds, a few percent of the speed of light, which is theoretically achievable with very advanced propulsion, a civilization could, over millions of years, colonize the entire galaxy. Just by sending out ships that slowly expand generation after generation, world after world, the whole galaxy is reachable in a time that is short compared to the age of the galaxy. So if there are lots of civilizations out there, and if some of them are millions or billions of years more advanced than we are, where are they? Why is there no sign? Why haven't they been here? Why don't we see enormous engineering projects, stars being used for energy, galaxies being rearranged? Why is the universe so quiet? This is a genuine puzzle, and many answers have been proposed. Maybe life is extraordinarily rare. Maybe the step from chemistry to biology, from non-living molecules to the first self-replicating thing that we'd call a life, is so improbable that it has happened only once or a handful of times in the entire observable universe. This is called the rare Earth hypothesis. And while it's uncomfortable for those of us who find the cosmos lonely enough already, it cannot be ruled out. Maybe intelligent life is common, but technological civilization is rare. Maybe intelligence arises, but most intelligent species don't develop the kind of technology that would let them communicate across interstellar distances or travel between stars. Maybe language and tools and society happen, but radio and rockets don't. Maybe civilizations exist, but they destroy themselves almost inevitably. Every civilization that gets advanced enough to be detectable also gets advanced enough to invent the weapons or cause the environmental damage that kills it, and they all burn out before they can spread. This one keeps certain people up at night for obvious reasons. Maybe they're out there, but communication is just too slow and they've given up. If the nearest civilization is 1,000 light years away, which even if there are millions of civilizations in the galaxy is quite possible simply due to the sizes involved, then a radio message takes 1,000 years to arrive and another 1,000 to get a reply. No conversation can happen on a time scale that matters to a civilization. Maybe they're there, but they don't want to talk to us, or they don't know we exist, or their form of communication is so different from radio waves that we're not even recognizing their signals as signals. Or, and this is the one I think deserves more attention than it usually gets, maybe the answer is simply distance. The universe is so large and the speeds achievable by physical objects are so limited relative to that scale that even if civilizations are common, they are effectively isolated from one another by sheer geometry, separated not by walls or intent or accident, but by an ocean of space so vast that crossing it is not a problem to be solved, but a fact to be accepted. Now, I want to come back to that conversation I told you about at the beginning, the fellow who told me I was being unscientific for thinking flying saucers are unlikely. Let me be very clear about what I was saying and what the actual scientific position is. I was not saying that life elsewhere is unlikely. I actually think life elsewhere is quite likely. The universe is almost absurdly large. The ingredients for life appear to be common, and we have at least one proof of existence, us. Life happened here. The argument that it happened only here requires you to believe that we are uniquely special in a universe with something like 10 to the 23rd power stars. That's 100,000 billion stars, and I find that very hard to swallow. I'm skeptical of arguments that put humanity at the center of things. History has not been kind to those arguments. What I was saying is that the idea of flying saucers, a physical craft traveling from another star system to Earth right now, in our era, that is what is extremely unlikely. And it's not unlikely because aliens are stupid or because they don't exist. It's unlikely because the distances are so enormous and the physics are so unforgiving. Here's a nice way to think about it. The fastest spacecraft humanity has ever built, the Parker Solar Probe, which uses the sun's gravity to whip around at enormous speeds, travels at about 37 astronomical units per year at its fastest. To get to Proxima Centauri, the nearest star, it would take over 7,000 years. If you want to get there in a human lifetime, say 80 years, you need to be going at something like 5% of the speed of light. To get there in a decade, maybe 40% of the speed of light. Now, there's nothing in the laws of physics that says this is impossible for a very advanced civilization, but the energy requirements are staggering. To accelerate a meaningful payload to even a few percent of the speed of light requires energy on a scale that dwarfs everything humanity has ever produced, ever. And you also have to slow down when you get there, which costs roughly as much again. And then the slightest dust grain at those speeds hits your spacecraft like a cannonball. Interstellar travel is not merely a technical challenge. It is one of the hardest things the universe permits. And even granting all of that, even granting that some civilization somewhere has solved it, they would then have to have chosen to come specifically here, to a smallish rocky planet orbiting a fairly ordinary star in the outer reaches of an ordinary galaxy. And they would have to be doing it right now in the few centuries since we've been broadcasting radio signals, which is a blink of an eye in cosmic time. For all of that to be true simultaneously requires a very long chain of unlikely things to all be true at once. And in science, when you have a very long chain of unlikely things all required to be true simultaneously, the conclusion is that the whole chain is very unlikely. That's not closed-mindedness, that's arithmetic. I want to tell you about something that puts this in perspective in a way I find just delightful. We have actually sent physical objects into interstellar space. Voyager 1, which I mentioned earlier, and its twin Voyager 2, along with Pioneer 10 and 11. These spacecraft have crossed the heliopause, the boundary where the sun's influence gives way to interstellar space. They are technically between the stars right now. Voyager 1 was launched in 1977. It is currently about 163 astronomical units away. In light travel terms, it takes about 22 hours for a signal from Voyager to reach us, not 22 years, 22 hours. We are barely out of the driveway. For Voyager to reach Proxima Centauri would take roughly 75,000 years at its current speed. It won't actually go there. It's headed in a different direction, but if it were 75,000 years, when Homo sapiens first walked out of Africa, we didn't even know stars had planets. By the time Voyager would reach the nearest star, we would need to have maintained a civilization and an interest in Voyager for more than 10 times the entire span of recorded human history. This is the scale of the problem, not the scale of the problem for us, the humans who just learned to fly 100 years ago. The scale of the problem for anyone, anywhere in the universe. Space is simply very big, and the rules of physics apply equally to everyone. There's a beautiful humility in that, I think. The universe doesn't care how smart you are. It doesn't give you a shortcut just because you're advanced. The distances are the distances. The speed of light is the speed of light for everyone. Now, there's one more thing I want to address because it comes up every time, and that is the idea of faster-than-light travel, wormholes, warp drives, exotic physics. In science fiction, this is how the problem is solved. You go through a wormhole and you're somewhere else instantly, or you warp space itself so that you're technically not moving through space. You're riding a wave of contracted space, and the speed of light restriction doesn't apply in the same way. I want to be honest with you about this. These ideas are not, strictly speaking, ruled out by what we know. Wormholes are consistent with the mathematics of general relativity. The Alcubierre drive, a theoretical warp drive, is a V to Einstein's field equations. The mathematics works, but the physics is another matter entirely. To create a traversable wormhole would require what physicists call exotic matter, matter with negative energy density. We have never observed negative energy density matter in any quantity remotely useful for engineering. It may not exist in the forms required. We don't know. To create an Alcubierre bubble would require amounts of negative energy that are staggering. Estimates suggest you would need something like the total mass energy of Jupiter in exotic matter to move a small spacecraft. And we don't know if exotic matter on that scale can exist or be created or be controlled. So when someone says, but maybe advanced aliens have solved faster than light travel, the honest answer is maybe, but we have no evidence that the required ingredients exist in manipulable forms, and the energy scales suggested by our best theories are so enormous that calling it a hard engineering problem understates the situation quite a bit. What I can say with confidence is this: we should not assume that faster than light travel is available just because we want it to be. In the history of physics, nature has not been obliging about giving us the shortcuts we wanted. We thought we could build machines that ran forever. Nature said no. We thought information could travel instantaneously. Nature said no. We thought particles had definite positions and velocities at the same time. Nature said no. Nature is under no obligation to be convenient for alien tourism, and our current best understanding of physics suggests that it probably isn't. So here's where I want to land, because I don't want to leave you feeling like this is a depressing story. It isn't. It's actually, I think, a thrilling one. Here is what we know. The universe is almost incomprehensibly large. It contains a number of stars so enormous that writing the number out in full takes about 23 digits. Why, almost all of those stars appear to have planets. A meaningful fraction of those planets appear to be in regions where liquid water is possible. Life on Earth, our one data point, seems to have gotten started pretty quickly once conditions were right. These are real facts. These are things we have learned mostly in the last few decades from telescopes and space missions and careful measurements. Here's what we don't know: whether the step from chemistry to biology is easy or fantastically hard, whether the step from simple life to complex life is easy or fantastically hard, whether the step from complex life to intelligence is easy or fantastically hard, whether the step from intelligence to technology is easy or fantastically hard, whether civilizations, once they develop technology, tend to survive for long periods or tend to destroy themselves. We don't know any of these things, not because we haven't thought about them hard enough, but because we haven't yet found the data to test our ideas against. The scientific process requires data, and on the question of life beyond Earth, we have been working with almost no data at all. That is changing. The James Webb Space Telescope is already beginning to look at the atmospheres of planets around other stars, searching for chemicals that might indicate biological activity. Future telescopes will do more. The search for extraterrestrial intelligence is listening to radio signals from thousands of stars. And I find this absolutely wonderful. Not because I'm sure we'll find something, but because we're actually looking. We're actually using the tools of science and real measurements, real instruments, real data to address one of the oldest and deepest questions human beings have ever asked. Are we alone? Is there anyone out there? Now, the flying saucers thing, the lights in the sky, and the abduction stories and all the rest of it, I want to be gentle but direct here. What I see in those reports is not evidence of alien visitors. What I see is the well-documented tendency of human perception to see patterns where none exist, to fill in the unknown with stories, and to mistake the unfamiliar for the extraordinary. Human eyewitness testimony is unfortunately one of the least reliable forms of evidence there is. Not because people are dishonest, but because perception is a process of construction, and we are very good at constructing things that aren't there. The question of whether intelligent life exists elsewhere in the universe is a profound scientific question, and it deserves to be treated with the same rigor and honesty we bring to any other profound scientific question. That means following the evidence where it leads. That means being willing to say we don't know when we don't know. That means not accepting a dramatic explanation when a mundane one is available. That means not confusing what would be exciting and wonderful to be true with what there is actual evidence to believe is true. The universe being full of other minds, other civilizations, other histories, that would be magnificent. I genuinely hope it is true. The universe being visited by alien spacecraft right now and the government keeping it secret, that requires a whole chain of implausibilities stacked on top of each other. And when I look at the evidence, I don't find that chain convincing. Here's the bottom line, and I want to say it clearly. The reason we haven't been visited, to the extent that we haven't been visited, which I think is fairly clear, is not that we are alone. It is not that we are special. It is not that there is something wrong with us or with the universe. The reason is that space is very, very large. Distances between stars are measured in years that light takes to cross them. The physics of moving matter through space at high speeds is brutally unforgiving, and the window of time in which we have been broadcasting our presence is cosmically tiny, about 100 years out of 10 billion years of galactic history. We have been shouting into the dark for the blink of an eye. Our radio signals, the earliest ones from the 1920s, have traveled about 100 light years in a galaxy, 100,000 light years across. We have informed about 1 to 10,000 of our galaxy that we exist, and only if someone near the expanding bubble of our broadcast happened to be listening. The silence we hear is not evidence of absence. It is evidence of distance. It is evidence of time. It is the universe being honest with us about its size. And honestly, when I think about it, I feel something that I can only describe as a very pleasant kind of awe. We are here on this little rock around this ordinary star in this unremarkable corner of the galaxy, and we have figured out it through the most careful and painstaking observation and reasoning how far away things are. We have determined that the universe is 13.8 billion years old. We have discovered that there are 2 trillion galaxies. We have found planets orbiting other stars by watching stars dim ever so slightly as those planets pass in front of them. We are a very young civilization asking the oldest possible questions, and we are actually making progress. That's not depressing. That is, if you'll forgive me, absolutely fantastic. The aliens are probably out there. They're just very far away, and that's the universe being the universe.